Let's talk about continuity. Now, when I talk about continuity, it's pretty much what you would think. If I talk about a function being continuous, or if I talk about continuity at a point, you know, something that looks like this. So, in other words, notice I drew this curve, and I drew it from here to here, you know, and let's say this is A, and this is B over here. And notice I drew this curve without ever raising up my pencil. So I would say that this function f, if that's what we're going to call this curve, this function f is continuous on that interval. So that's the way you can think of it. I started here, including this point. I never raised my pencil, and I finished over here at b, and I would say, okay, that function is continuous on that interval. Well, we want to be a little more rigorous than that when we talk about what continuity is. Now, in fact, we're going to use limits. Now, notice, let me just find a point here. I'll call this point C, or this number C. C is between A and B. So, since C is part of this interval where I'm continuous, here's what we mean if we say, we'll do this. We'll talk about continuity continuous at a point, and then if you have continuity at every point in an interval, then we say, okay, the function is continuous on the interval. But here's what we mean when we say continuity at a point here. Notice that f of c exists. Okay, it exists, right? It's in there. And also notice that the limit as x goes to c exists also. See? So see, what I did was I had a continuous interval. I had an interval over which this function is continuous, and I just picked a point in there and I said, let's look at some of the characteristics of that point. Well, the point exists. You know, this point right here is c, f of c. The limit exists, as you can see. And in fact, the limit is exactly the same as just plugging in the function, or just plugging it into the function. So whenever this happens, that's when you know you have continuity at a point. So we say that f of x is continuous at x equals c. See? Because this is true right here. Okay? Now, okay, so that's continuity. And if you have continuity throughout the whole interval, we say it's continuous on the interval. So it's a really simple concept to grasp. Now, what makes something not continuous? Well, let's look at some examples. Let's suppose we've got this curve, and I'll just put a little hole right there. Now, and of course this is A, and this is B, and this is C. Notice that f of c does not exist. There's a hole there. However, the limit does exist. So this is a situation. This is a situation where you have the function itself doesn't exist. The limit exists, but the function doesn't exist there. And notice what has to happen is the function has to exist and the limit has to exist. They have to be the same. So here's an example where you have a hole. This is a hole. And we're going to say this is a removable discontinuity. A removable discontinuity. Because I could remove this discontinuity just with one point. I could just put a point in there and remove it. Okay. Now let's look at another one. Let's suppose, let's see here. Let me make a nice, beautiful graph here. Here we've got a hole again. This is A, and this is B. And let's suppose we put something down here, a dot. Okay? So here's an example where we would say this. We would say, well, f of c exists. See? Because right there. Okay? F of c is that point right there. However, the limit exists. Okay? So f of c exists and the limit as x goes to c exists. However, the limit is not the same as f of c. And once again, notice I could fix this just by putting a point there. So this is said to be a removable discontinuity. A removable discontinuity. Okay, so we have two examples here of removable discontinuities. Now, let's look at another one here. Let's suppose, let me draw a picture here, and let's suppose I start here at A. I come up here, this is C. Okay, now this is another example of a discontinuity. Notice it looks a little different than these. It looks a little different from this one and this one, where I could fix this just by putting one dot there. It's like this curve on both of these. It's like this curve gets right up to this point, and then it breaks the continuity, steps over, and then picks up on the other side. Well, this one is a little bit different because notice that f of c exists. However, the left-hand limit is different from the right-hand limit. Therefore, the limit itself does not exist. Does not exist. So here we have a situation where we have a discontinuity, and this is called a jump discontinuity. This is called a jump. Okay, so we have removable discontinuities and we have a jump discontinuity. Okay, so remember that. If you can fix it, if it's just you're drawing this graph and you just can fix it with one little point there and then pick it up, continue on your business, if you can do that, it's removable. So it's like a little hole in the graph. However, if you've got a situation where you step up, you go to a whole nother level, that's a jump discontinuity. Okay, so that's a jump discontinuity. Now let's look at another one here. Okay, let's suppose that we've got an asymptote here. And I start here, come up here, maybe pick it up on the other side over here. So here's A and here's B. And let's suppose this asymptote is at C. So this graph goes off to infinity here at C. Well, we say this is an infinite discontinuity. This is an infinite discontinuity. So what we want to do is we want to look at examples of each one of these types of discontinuities, removable, jump, and infinite. So okay. So first of all, let's look at a removable. So let's suppose we've got f of x equals, let's say x squared plus 5x plus 6 all over x plus 2, like that. Now, we want to find if there's any discontinuity here. Well, we know that if there's a value of x that we can put in here that will make this denominator 0, that's going to be a discontinuity. The function is going to have, there's not going to be a graph for that part. Okay, there's no point. So what we need to do to find a discontinuity is we're going to set the denominator equal to 0. To find out if there is indeed some x value that if I put it in here, I'll get a 0 in the denominator. And sure enough, we get x equals -2. Now this is where a discontinuity occurs, at x equals -2. We know this because putting a -2 in this function, we don't get, the function doesn't exist there. Okay? Now the limit may exist there, but we know the function doesn't exist there, therefore there's a discontinuity. Now our question is, really, is this, what kind of discontinuity is it? Is it removable or maybe infinite? Now, an infinite discontinuity would be if this x equals -2 is a vertical asymptote. A removable discontinuity would happen if it divides out with the top. So here's what we do. We do some investigating. I'm going to factor the top. And, okay, so I've got it factored. Now notice what happens then. This and this cancel. This thing that caused the discontinuity has been removed. I've divided it out. So this is a removable discontinuity. A removable discontinuity. That's what that is. Okay? Because it divided out. So what we do, to find the discontinuity, set the denominator equal to 0. Then see if it divides out. See if what makes the denominator 0, see if that factor will divide out. If it divides out, it's removable. Now let's look at another example here. Let's suppose that we've got another function, and let's suppose it looks very much like this function. And down here we have, let's say x squared minus 4. Something like this. Okay? Now, once again, we want to set the denominator equal to 0 so that we can determine, find the discontinuity. So I'm going to take the x squared minus 4, set it equal to 0, and solve it. And of course, when we do that, we get x equals plus or minus 2. So these are our points of discontinuity. We've got x equals -2, x equals +2. So these are discontinuity. This is where our discontinuities occur. Now we want to find out if they're removable or infinite. So let's see if these factors divide out. So I factor the top. Okay, factor the bottom. Now notice this and this cancel. They divide out. Now x plus 2, that's where I got this place of discontinuity. When x equals -2, we had a discontinuity, but that factor that gave us that divided out. See? So we say that this one right here, this is removable. Now this one, x minus 2, that gave us x equals 2, that didn't divide out. So this one right here, this is infinite. Okay? That one's infinite. Okay? So this one had both a removable and an infinite discontinuity. Now let's look at this one. Let's look at another one. Let's look at a piecewise function. Let's suppose that we have, let's say 2x plus 1 for x less than or equal to 1, and 3x minus 4 for x greater than 1. And let's see if we can find the discontinuity for this piecewise function. Now, you realize that 2x plus 1, that's continuous every place. of itself. I mean, just by itself, it's continuous every place. It's just a line. The 3x minus 4, that's continuous every place. It's just a line. Where there might be a discontinuity is right here at 1, where we transition from 2x plus 1 to 3x minus 4. So I want to find out if there is indeed a discontinuity there. So I'm going to plug in this boundary number here into 2x plus 1. And I get a 3. Now I'll plug in the boundary number into 3x minus 4. And I get a negative 1. Ooh, those are not the same. Those are not the same. What we've done is we were going along here, and then we jumped down. We ended up at 3, and then we jumped down to negative 1. See? So that is a jump discontinuity. A jump discontinuity. Now, this is not the only way you can have a jump discontinuity. I'm just looking at, the basics, some basic examples to familiarize you with the terms and how these things can occur. But there are lots of different ways you can get a jump discontinuity, lots of different ways to get a removable discontinuity, and so forth. Okay, so now, when we talk about, so we've got removal, we've got jump, we've got infinite discontinuities, and we've been talking about continuity in general. In other words, we said, let me just go back and draw a picture here. We've got a function like this, and we said this, I drew this without ever raising my pencil, including the endpoints. Notice I've got the endpoints closed in. Now, this right here, okay, so we've got this function that's continuous on this entire interval from a to b. Now, this is a closed interval, including, when I say closed interval, I mean at a. It includes a. So this is continuous on this whole closed interval. That means it's continuous everywhere in here, plus at the endpoints. Now let's look at another example here where the endpoints are not included. Okay? So here's A, and here's B. Now this is continuous on the open interval, because notice the endpoints are not included. Okay? The endpoints are not included. So notice, we've got a difference here. Continuous on the closed interval, continuous on the open interval. The difference is the endpoint. So look, I said earlier that if you have an interval, and you talk about it being continuous throughout that interval, that means that every value in here, every x you choose between a and b, you've got this situation. You've got the limit as x goes to c of f of x is equal to f of c. That's true for every c in here. But what about at the endpoints? To say that something is continuous on the closed interval, what does that mean? Well, here's what it means. It means this, that the limit as x goes to a from the right is also equal to f of a. In other words, the right-hand limit. This is true. And also, the limit as x goes to b from the left is equal to f of b. So here's what we have. You have continuity at every point between a and b on the open interval, if this is true. Now, if you want to say, okay, it's also continuous on the closed interval, that means you're including the endpoints. That means, additionally, this condition is true and this condition is true. So there you have continuity on the closed interval. So if you have continuity in a closed interval, it means you have continuity in the open interval plus continuity at the endpoints.